Okay, this is exam 1 for Physics 102, spring 2017. It says the up quark has an elementary charge of plus 2/3 e and the down quark has minus 1/3 e. What combination of these quarks make up a proton? Well, a proton, of course, has a charge of plus 1 e, and so I need some combination of these, and the only combination of these is 2/3 plus 2/3, that's 4/3, minus 1/3. There is no other combination of these that will give you a charge of 1 fundamental unit. So this is a up, up, down. So up, up, down. B is the right answer. This diagram shows 3 heavily charged plastic cubes. The net force on B is shown. If B is negatively charged, what is the charge on A and C respectively? Well, in order to get this kind of charge, or this kind of force vector, net force vector, I need a force in this direction and a force in this direction. There's no other combination of vectors that will give you that net force. These aren't necessarily equal vectors. In fact, they're not equal vectors, but that's not necessary for the problem. So in order to get this to be opposite, or repulsive, that needs to be negative. In order for this to be attractive, this needs to be positive. So A is negative, C is positive. A is negative, C is positive, so that's C. When you rub your feet on the carpet, your body becomes electrically charged. What has happened? You gain electrons from the carpet. You don't deposit electrons on the carpet. You don't gain protons from the carpet. You don't deposit protons on the carpet either. Which of these is a property of charge? Charge is quantized. Charge is conserved. Charge is not directional and it's not immovable. So 1 and 2. Is this statement true or false? The electrostatic force helps to hold together heavy nuclei. In heavy nuclei, you got a bunch of protons, and then you got a bunch of protons. Well, not neutrons. The protons are all positively charged, the neutrons are neutrally charged, and so you have, these things are really close together, you have vast electric forces trying to pull this thing apart. So the electric forces do nothing to hold the nuclei together, especially these heavy nuclei, because they're all repulsive forces. And so that answer is B, false. In fact, it's the strong nuclear force that holds them together. To start a car engine, the car battery moves 5 times 10 to the 20th electrons through the starter motor. How many coulombs of charge were moved? Well, I have 5 times 10 to the 20th electrons, and there are 1.6 times 10 to the minus 19 coulombs per fundamental unit. So let's see, that's 5, that's 8, that's going to be 80 coulombs. It's going to be negative 80 because there are electrons that it's moving through. The force between two charges, which are separated by 4 meters, is 18 newtons. If the two charges are moved further to a distance of 12 meters, what is the force? Well, my force is given by this, KQQ over R squared. I'm going from 4 meters to 12 meters, so I'm increasing this by a factor of 3. So my force is decreased by a factor of 9. It was 18. 18 divided by 9 is 2. 7 is A. Two identical charges, 2 meters apart, exert forces on magnitude 4 newtons on each other. The value of either charge then is what? So I have two charges. They're 2 meters apart. And I have 4 newtons. Or we don't know if they're attractive or repulsive. That doesn't really matter. So I say 4 newtons equals 9 times 10 to the 9th. This is Coulomb's law. Q times Q. Or you know what? I'm just going to get rid of this. I'm going to call this Q squared because they're identical. Divided by R squared, that is 4. That's 2 meters squared. So I get 16 divided by 9 times 10 to the 9th. And then the square root of that. And that's 4.2 times 10 to the minus 5 coulombs. So D is the right answer. Two separate charges, each of which are 4.2 times 10 to the minus 5. 2 electrons and a proton are spaced equally far apart in a line, as shown. So that means that, this distance is equal to this distance. What is the direction of the net force on the second electron? All right, so let's see. This is negative, this is negative, this is positive. I have a force on this electron due to the proton that's in this direction, and due to that electron, it's also in that direction because it's a repulsive force. So it's going to be, what's that, to the right? 9 is B. What is the magnitude of the force acting on the charge Q2? the middle one in this configuration. Well, you could go through and calculate this, but let me show you. I know that F is equal to K QQ over R squared. And I also know that the one due to this charge is going to be in this direction, and the one due to this charge is going to be in this direction. Now let's look at how these charges are different. Let me rewrite. I'm just going to sort of expand this. Looking at this charge, it has a charge that's 4 times that of the other. So I'm going to put a little 4 in there. And it has a distance that's twice as far away as the other. See, 2 meters versus 1 meter. So it's twice as far away. So I get a 2 squared and a 4. So these are effectively going to cancel one another out. So if you go through the calculation and you just calculate the forces, you'll find that this force is equal but opposite to this force. So for number 10, the answer is B. You could go through and calculate it, and that's fine, doing the K QQ over R squared, but that's not really necessary. A 6 microcoulomb charge is placed at the origin, and a second charge is placed on the x-axis at 0.3 meters. The force is 5.4 newtons. What is the value of its charge? Okay, so I have one charge here, one charge here. This one is plus 6 microcoulombs, and then this is 0.3 meters away. And the force is 5.4 newtons in that direction. So first of all, I know that this has to be a plus Q. So I can get rid of C and D. So I'm looking at either, looking at either A or B. This is similar to the previous question we had. I have 5.4 newtons equals, oh shoot, sorry folks. Pause. All right, so, oh gosh, sorry. So 5.4 newtons is K QQ over R squared. That's 9 times 10 to the 9th. Q is 6 times 10 to the minus 6. Q divided by 0.3 meters squared. And then I solve this for Q, and I get that Q is equal to 9 times 10 to the minus 6 coulombs. So that is A, 9 microcoulombs, and we know it's positive, as I said. Number 12, what is the magnitude of the electric field? Okay, well first, let's just sort of sketch this in, because in the next problem we're going to need to find the direction too. But due to this charge, which is positive, my electric field is in this direction. Due to this charge, it's going to be in this direction and a lot bigger. Okay, so let's figure out, I'll call this one E1 and I'll call this one E2. E1 is equal to 9 times 10 to the 9th. E, remember, is KQ over R squared. So I have 9 times 10 to the 9th. Q is 32 times 10 to the minus 9 divided by R squared, which is 2 meters squared. So I can cancel this, get 8 up here, cancel these out. I get 9 times 8, which is 72 newtons. Now, if you're really astute, you can probably go ahead and hone on some of these answers, and you might even, if you're pretty clever, you can get up with A. But let's go ahead and figure out what E2 is. A is going to turn out to be the right answer. E2 is going to be 9 times 10 to the 9th times 4 nanocoulombs, 4 times 10 to the minus 9. And then we'll find that this electric field is a lot smaller. It's just 9 newtons. So I have one really big vector in the negative y direction, and then one really small vector in the negative x direction. And so if I do the square root of 72 squared plus 9 squared, that's equal to 73. It's basically the same length. The hypotenuse is basically the same length as the side. Now, what is the direction of the electric field? Well, let's look at this. So I know that that electric field is going to, come down in this direction. I want to know this angle. I always measure my angle from the x-axis. And so theta is the inverse tan of the y over the x. That's 72 over 9. That's opposite over adjacent. 72 divided by 9 is 8, of course. So the inverse tan of 8 is 83 degrees. So this is 83 degrees. Let's look at these. It's not that. It's not that. 83 degrees below the negative x-axis. It's not that one, and it's not that one. So A is the only reasonable answer. And the correct answer, in fact. This figure shows two spheres that each have a charge. If Q2 has a charge of magnitude 4 coulombs, what is the charge on Q1? Well, first of all, this has to be negative, so that means this is positive. It's negative because these field lines are going into the charge. Field lines always go into a charge. They come out of a positive charge. They go into a negative charge, out of a positive charge. And then I count the field lines. I have 1, 2, 3, 4, 5, 6 over here. 1, 2, 3, 4 over here. So my ratio of charges is 6 to 4. Oh, well, look, I have 4 coulombs here, so I must have 6 coulombs over there. If it was different, like I could also say, I take the ratio, 6 over 4, times 4 coulombs, multiply the ratio times the original charge, and then that gives me the left charge. So number 14 is C. Consider this configuration of charges. At what point is the electric field equal to 0? Well, let's take a look. So let's start over at E. Due to this charge, the electric field is big and in this direction. Due to this charge, it's small and in this direction, because I'm further away from that smaller charge. So that's obviously not it. Where's my eraser? All right, now, let's look here. Due to the minus 4Q, my electric field is in that direction, and due to the plus 2Q, it's in that direction. So the electric field vectors all throughout this area are all going to point to the right. They'll change in magnitude a little bit, but they're all going to point to the right. So that must give the answer as A, but let's just sketch this out so that we're clear. Due to the plus 2Q charge in that direction, and due to the bigger charge, from which I'm farther away from, it'll be in that direction, but it's limited because of the distance. I'm further away from the bigger charge, so the electric field is limited, and it doesn't overwhelm the electric field from the smaller charge. So for 15, the answer is A. Where you direct a beam of electrons between two charged plates. This is actually really common in various instruments that we use. And also, in electrical devices that we use, like the old television, which probably don't watch anymore. But anyway, the electron beam comes through this electric field. The electric field runs from positive to negative, just as we talked about. Now, the force on electrons is opposite the force on protons. Like if this were protons, they would go in that direction, but it's not. It's electrons. They'll go in this direction. And you can think of it as, well, these negative charges are repelling those charges and these positive charges are attracting them. If you want to think of it in that way, that's fine. But it's probably better to think of it in terms of the electric field. The electric field is down, so the force that the electron feels is up. It's opposite the force that a positive charge would feel. Consider this configuration of charges. At the origin, what quadrant does the net electric field vector point? All right, so right here, where does the net electric field vector? So due to this charge, the electric field vector is in this direction. Due to this charge, the electric field vector, see, it's a little smaller and it's in this direction. And then due to this charge, the electric field vector is bigger than either one of those two, and it's in this direction. So my net electric field is going to be somewhere over here in the fourth quadrant. So for 17, it's D. All right, I think this 18 was actually from your tutor. Two uniform electric fields are superimposed. The first is 12 in the positive x direction. Let's just draw our coordinate system. Hey, let's use light blue. 12 in the positive x direction. So I have 12 newtons per coulomb. And then I have 8 in the negative y direction. 8 newtons per coulomb. And I want to know what angle will a positive test charge, so if I put a plus q here, what angle will it accelerate in this combined field? What direction will it go? That's really the great thing about electric fields, is you can use them to move charged particles around and to think about how these charged particles move. And that's important in the human body, and it's important in various instruments that you might use in the future. Now, we know it's going to go down here, so we can get rid of some of these. Like we can get rid of this one, but we can't get rid of the others because it has to go below the x-axis. And to find that answer, we say the inverse tan of opposite over adjacent. The opposite is 8. The adjacent is 12, so 8 divided by 12, inverse tan of 8 divided by 12, and I get 34 degrees. So it's 34 degrees below the positive x-axis. Number 18 is B. If the distance between two negative point charges is increased by a factor of 3, the resultant potential energy is what factor times the initial potential energy. So if I have two charges, they have a certain amount of energy. But what if I space them further apart? Well, as you pull them further apart, the forces that are acting on them become less so. And therefore, they have less potential energy. That potential energy is given by this, U equals K QQ over R. Be very careful with these. We have lots of very similar equations that we're using, but this is our potential energy. And if I increase R by a factor of 3, that means that my energy is decreased by a factor of 3. So B is the answer for 19. All right, this diagram shows collection of charges. At what point is the potential equal to 0? Is it A, B, C, D, or is it none of these points? Well, let's see. At point A, what I'm looking for is points where the distances to the oppositely charged charges are the same. And in that case, look, we have different distances to the 1 and the negative 1, as well as the 2 and the negative 2. So in those cases, those potentials don't cancel out. Let's look at point B. Let's see, those are the same distances, so I get V equals 0. Those are the same distances, so I get V equals 0. And then similarly over here, that's V equals 0. So in all these cases, the potential is equal to 0 for space B. So that's number 20 is B. This figure shows two charges. What is the potential at point P? All right, so to find the potential at point P, I do the sum of the individual potentials, which is the sum of KQ over R for each individual particle. So I have, let's do it for this one first. K times, well, shoot, let's just go ahead and write it all out. 9 times 10 to the 9th. Negative 32 times 10 to the minus 9. Because it's a negative charge. Remember, these scalar quantities, I'm always going to include my signs for the charges. That includes the potential energy, U, as well as the voltage, or the potential, V. This is divided by R, which is 2 meters. Plus KQ over R, I'll write it down here, 9 times 10 to the 9th, 4 nanocoulombs, divided by 2 meters. And so let's see, I can get rid of some things here and here. This becomes negative 18. This becomes 2. So we get 9 times negative 18 plus 9 times 2. What's that? 9 times 16? 90, 54. Well, let's see. I have a mistake here. Let me take just a break. I'll find it where it is. I'll come back. Okay, I see. I made a mistake up here. Sorry about that. You've probably already noticed. This shouldn't be 18. This should be 16. I just said 32 divided by 2 right here and right here. And so this becomes 16. 9 times 16, 90, 54 minus 18. That becomes 1 minus 126 volts. I think that's right. Number 21. It's, oh shoot, that's not right. Hold on. Let me take another break. I'll be right back. Okay, that is right. My key was just wrong. So D is the right answer here. So number 21 is D. All right, what potential energy is contained in that configuration of charges? So remember, potential energy is U equals KQQ over R. So I need to figure out what is the distance between these two charges. I have a right triangle here, 2, 2, and I need to know what is this distance. So to do so, I say R is equal to the square root of 2 squared plus 2 squared. That's the square root of 8, which is going to be 2.8 meters. And then U is going to be 9 times 10 to the 9th. Q, which is 4 times 10 to the minus 9. 32 times 10 to the minus 9. divided by r, which is the distance between them, which is 2.8 meters. And this works out to be 4.1 times 10 to the minus 7 for 22. How is the potential energy related to electric potential related to electric potential energy? Remember, V is energy over charge. Energy over charge, or you could say that it's electric potential energy over charge. So that is this one, B. Membrane walls of living cells have surprisingly large electric fields across them due to separation of ions. Right, so we get these, you know, the potassium and the sodium and all those business. They're separated, and they are fairly thin, 6 nanometers. And I want to know what is the electric field strength then across those membrane walls that causes those ions to move back and forth. It's an immense electric field that's set up by this potential difference. You know what, if you're not really sure how to work this, look at the units. I want to know the voltages. I have a distance. I have an electric field that's in volts per meters. So you might just, not even looking at your equation sheet, say that V is equal to Q times E. Excuse me, E times X. That it is equal to E times delta X. And in fact, that is on your equation sheet, but you could just look at the units here and probably get to the right answer. The electric field is 6.0 times 10 to the 6th. That's in volts per meter. And then this is 6 nanometers, or 6 times 10 to the minus 9 meters. Notice my units cancel to give me volts, which is what I want. This is going to be 36 times 10 to the minus 3. So our 0.036, B is 24. Positive charges move from high to low potential. Think about, you know, my parallel plates. If I have a positive charge, it's going to move in this direction. This is my high side, this is my low side. Or you can also think about it in terms of like a mountain. This works for positive charges, it doesn't work for negative charges. But on a mountain, if you have something here, it will tend to move from high to low potential energy, or potential. We don't really use that term in this class, or gravitation, but it is a term. So positive charges will move from high to low potential. How are E-potential lines related to electric field lines? They don't always encircle. They're not always parallel. In fact, they're never parallel to field lines. They are not independent. They are perpendicular, and they are not always stronger. All right, so I think that was the end.